Let me get my screen up. All right, well, thank you everyone for joining us today for the National Road Research. Research pays off. Today we'll be going through a number of different presentations looking at the long-term research that's going on here, through the NRRA. We'll be starting out this morning from 9 to 11. We'll be talking about determining the criteria for recycled aggregate base and large stone subbase, followed by talks on fiber reinforced concrete. Then at 10, we'll be talking about reducing cementitious material and optimizing the concrete mixtures. And then following up at 10:30, maintaining poor pavements. So we'll have this session in the morning, then we'll have this session in the afternoon from 1 to 3 o'clock. So again, join in when you have time or when you have interest. It's open, so any time is great. So today, start out from 9 to 9:30. We're going to start with Bora Cetin. He's going to be talking about determining pavement design criteria for recycled aggregate base and large stone subbase material. Again, work is being done through the geotechnical team. And Bora, if you'd like to go from there.
All right. Thank you, Ben, and thank you very much, everybody, for being available this morning.
So, Bob, will you give control over to Bora?
Everybody,
he's a presenter. He can take control.
Yep. Everybody sees my screen now?
Getting there. Yeah, now we do.
Okay. All right. Thank you very much, Ben, for the introduction, and thank you very much for everybody being available. So our project is determining pavement design criteria for recycled aggregate base and large stone subbase. This is a project that is started almost a year ago. By December, it will be almost a year. And this is a collaborative work between two institutions, between two universities, and of course also with the NRRA group. Iowa State University, I'm the PI of the project, Bora Cetin, and I have 3 co-PIs, Ashley Bass, Dr. Ceylan, Dr. Zeng, and our PhD student, Haluk Sinan Çoban, is working with us. And at University of Wisconsin, we have 2 co-PIs, Dr. Lykos, Dr. Adil, and currently, a couple of months ago, we also have a visiting scholar from Sakarya University working with us on this project. Again, we would like to appreciate the support of the NRRA members, our agency partners, and industry partners. We really appreciate your support and also be able to fund this project. And this is a brief outline of our presentation today. I will try to be fast as much as possible. We collected a lot of data, and we try to digest all of that in 20-25 minutes, hopefully in 20 minutes. So we will talk about the objectives and why this research was necessary, and what we have done so far, a summary of the results quickly, and what we have been working currently. So the motivation of this work is really the main idea is the virgin aggregates. We start using these virgin aggregates tremendously in the amount of required virgin aggregates and the demand for it increased significantly, and as a result of that, high quality aggregates are depleting. And these map on the bottom right corner, the shaded areas, colorful and shaded areas are the places where you have aggregate in limited occurrence, and even though you have these aggregates, majority of them have low quality compared to the rest of the nation. So reuse of recycled materials such as recycled concrete aggregate and recycled asphalt pavement is a good alternative way to use in pavement foundation systems. And in this project, we used 3 different materials, 2 recycled materials, recycled concrete aggregate and recycled asphalt pavements. And recycled concrete aggregates can come from old failed concrete pavement surface, which is most of the time OH pavement surface, concrete surfaces are being crushed in a certain size and placed in place during construction as a base layer or sub-base layer. But also there are stockpiles of of RCAs that are collect the material, demolished concrete collected from all sort of structures. And recycled asphalt pavement is basically failed and aged asphalt pavement surfaces. And recently means like over the last decade or two, large stone subbase become interest as a subbase layer especially. And there are currently 3 DOTs have some sort of guidelines for this, Idaho, Illinois, and Wisconsin DOTs to provide some guidance how to use the large stone subbase materials. And the size of these materials changes from 3 inches to 6 inches, but there are some particles as big as 1 foot diameter in size. And one of the main advantages of these, the energy consumption decreases significantly, less single crushing operation as opposed to regular aggregate, conventional aggregate and recycled concrete or recycled asphalt pavement aggregate crushing process. As a part of this study, we had 2 tasks. For task 1 was the literature review summary, and the task 2, I mean, we have a total of 8 tasks, but the first 2 tasks were literature review and tech transfer preparations for recycled concrete aggregate, recycled asphalt pavement, and for the large stone subbase. And overall in the literature, the summary was angularity of the RCA was higher, and hydrophobicity and permeability information like RAP materials, recycled asphalt pavements, were higher than RCA materials. And in terms of stiffness and strength, RCA and RAP, in terms of stiffness, either equal or superior provide performance equal or superior to virgin aggregates. And in terms of strength, RAP in the literature tend to have a little bit lower strength compared to RCA and VAs. And in terms of durability, RCA with freezing and thawing cycles keep gaining strength. On the other hand, RAP and virgin aggregate had either similar, or RAP sometimes had a superior performances. So I will be happy to provide more detailed information about this later on if any further questions on the literature sides. So research motivation was the variability and uncertainty of these RCs and RAP materials. It really changes from location to location, so it is always requires some more analysis and tests. And the limitation, large stone subbase have been studied by some of previous researchers, but there are still limitations because of the size. The lab test cannot be really conducted on these materials, and there are some inconsistencies with the design methods and construction specifications between agencies or even contractors who are working on this area. And there have been studies, especially by MnROAD, again, the prediction of the engineering properties of these materials from simple index properties. But we would like to enhance that knowledge more. And on top of that, large stone subbase, it has not been really studied in terms of prediction of their engineering properties from their index properties. So this research will also bring that information on the table. And these are the 3 main objectives of this study. We have 3 goals mainly, and all of them have different subtasks. Like first, understanding their both lab and field performances. Second, try to understand their index properties and kind of relate that to laboratory test results and field stiffness strength test results. And the third one is to really come up with a good pavement design about the use of these 3 different materials and try to understand its cost benefits, and also do some life cycle cost analysis, looking into the cost benefit of it, and also looking to the some of the environmental sustainability assessment related things. So we had a total of 9 tasks, and we completed the first 3 tasks. We revised the task 3 based on the comments of the NRRA Geotech team. So task 4, 5, and 6 are continuing process. So we're currently working on those tasks. So I will mainly talk about the results of the task 3 on this project. So we have test sections, 11 test sections in the low volume road side of the MnROAD. And this is kind of schematic pictures of the test sections from our construction report. And again, we have total of 11 test sections. We have recycled aggregate bases and large stone subbase that are built with the higher thickness, and 4 large stone subbase with geosynthetics, with different types of geosynthetics or combination of geosynthetics, have a large stone subbase, and then put class, and on top of the large stone subbases we have the class 6 aggregate, conventional aggregates, and class 5Q conventional aggregates, and all test sections are built with 3.5-inch HMA hot mix asphalt. So recycled aggregate bases, these are the cell numbers 185, 186, that the one of the, and the cells 188, 189. Cell 188 is the test section that has a base determined with coarse earth recycled concrete materials, and cell 186 has the base layer built with fine recycled concrete aggregate, and cell 188 and 189 are the cell 188 built with conventional class 6 aggregates for control material, and cell 189 is a combination of RCA and RAP placed in as a base layer in cell 189. And one main difference between recycled aggregate base test sections and other test sections, we have sandy granular barrow material as a subbase, and cell 185 and 186 have sand subgrade, while 188 and 189 had clay loam subgrades. And large stone subbase, again, we have 7 different large stone subbase test sections. So cell 127 and 2027 have 18-inch thick large stone subbases. The idea was this: they wanted to, the geotech group wanted to build one of the large stone subbases in 2 lifts instead of 1 lift, but due to the construction difficulties, it didn't really work out well in terms of compaction and that sort of thing. So we have 2 identical test sections that has large stone subbases that is a height of 18 inches. And 4 of the large stone subbase test sections have the geosynthetics installed between the subgrade and the large stone subbase layers. And TX is the triaxial geogrid, and the TAGT is the nonwoven geotextile, and BX represents the biaxial geogrid. So we have sections that are built with triaxial geogrid and biaxial geogrid only, and combination of these geosynthetics. And the last cell that we deal with has a 9 inches thick large stone subbase, has no geosynthetics. And also geotech team installed environmental monitoring sensors such as thermocouples, moisture, water content sensors, and some dynamic pressure cells, geophones, and dynamic strain gauges. And these are the kind of plane view and the profile view of these sensors placed in the under the test sections. Majority of the sensors are placed in the recycled concrete aggregate bases. Cell 185 through 189 are all the recycled aggregate bases test sections, and we have one on the large stone subbase and at the end of the geosynthetic test section. And the sensors are placed on the outside lane, not in the inside lanes, and we have thermocouples especially placed in all the way to up to 70 inches, which is almost 6 feet depth. And we have moisture sensors that are close to the ground surfaces. And the data so far for test 3 during construction collected nuclear gauge density data and moisture content data, DCP, lightweight deflectometer, gas permeometer results, intelligent compaction data, and falling weight deflectometer data. So I will summarize those results for the group here. And this figure kind of shows the in-situ dry density right after compaction. And the blue boxes are showing the subgrade, representing the subgrade characteristics, and red boxes are showing the density, dry in-situ dry density for the base layers. And as you can see, subgrade stiffness, we have the subgrade nuclear gauge density data only for the recycled concrete base layers. In terms of density of the base layers, RC, we don't see any consistent trend. For the moisture content values, the RCA materials tend to have higher, RCA-based materials tend to have higher moisture content during the construction, and subgrade were compacted on the lower moisture content values. And the base layers on top of the limestone subbases have very close or a little bit slightly lower moisture contents than the RCA test sections. And we have the gas permeameter test data, which is kind of giving us an idea about the permeability of the base layers of each test section. So coarse RCA, as expected, had higher permeability, which is expected. And on the other hand, fine RCA and the class 5Q conventional aggregates that are placed on the large stone subbase test sections have the lowest permeability, which is again expected. Permeability is directly correlated to the grain size distribution, and these results, based on the saturation level of these test sections, therefore moisture content has a great impact on the data that we collected here. And here in the S ladder here, we kind of provide the saturation levels of each of these test sections. And lightweight deflectometers on the subgrade and on the base layers of the test sections are shown in here. Again, red boxes are showing the performance of the base layers, and blue boxes are showing the stiffness of the subgrade layers. What we can say based on the LWD after results after compaction, the coarse RCA and fine RCA test sections provided the highest stiffness. And then conventional limestone class 6 and RCA wrap is a little bit lower than the coarse RCA and fine RCA, but they provide almost identical with the 12-inch, 18-inch thick large stone subbases. And we see some little bit slight decrease. We see some decrease with the base stiffness on the large stone subbase test sections with geosynthetics. And then the intelligent compaction data, it was collected by Ingios and the University of Texas at El Paso and shared with us. And basically after the preliminary IC mapping occurred, and on top of the cyclic stress-dependent residual modulus, automated plate load test was conducted on the test sections at different plate contact stresses. And the analyses were done in two ways. One is a composite and one with the layered analysis. In the composite analysis, we assume the entire base, subbase, and subgrade layer as one composite layer. On the other hand, with the layered analysis, we calculated base and subbase stiffness and subgrade stiffness different from each other. So composite, the results are showing in the white boxes, and again, base subbase is in red boxes, and subgrade residual modulus data are shown in the blue boxes. And again, as the LWD results, both composite or regardless of the analysis type that we saw, the test sections built with coarse RCA and fine RCA showed the higher residual modulus values. And 18-inch thick large stone subbases, especially cell 127, provided the third highest performance in terms of residual modulus. And then class 6 conventional aggregate and the RCA wrap mixes were very identical in terms of their comparisons. And the large stone subbases with geosynthetics performed relatively little bit lower, provided lower stiffness. And one thing that we wanted to point out in this, if this is consistent with all LWD, FWD, and intelligent compaction data, to see the benefit of geosynthetics, really you need the FWD or these residual modulus, the APLT and LWD test, the load that we apply is not adequate to really see the contribution of the geosynthetics. So we don't want to get any conclusions that geosynthetics didn't really contribute. And it, in fact, it really contributed during the construction stage because subgrade was too loose and geosynthetics really hold the large stone subbase layers pretty well intact. But to see the real contribution of these geosynthetics, we really need to apply different load, much higher loads than what FWD or automatic plate load test or LWD tests it can apply. And falling weight deflectometer, thanks to, again, MnROAD test facility, they have been conducting and collecting this data for us. And there are different loading steps for before paving and after paving. And before paving, again, we did the composite analysis and also layer by layer analysis, and we conducted FWD analysis both for semi-infinite and the depth rock or water table analysis. Today we will only show the depth rock analysis, and these are the water table levels that we obtained from the software, and we're also working with the MnROAD test facility to get the water table levels, how it changes over the time. So depending on that, the task 5 results the analysis, we may use different water table levels. And then this is the graph that shows the maximum deflections before paving on the base layer test sections and 3 different loads. And we showed here, just to show, we did the analysis for both 3 loads, but the first 2 loads are really for the seeding of the test section. So when we make the main analysis, the comparison analysis, we compare the third load level results. And here, the results are showing the elastic modulus values before paving for composite test sections and again layer test for the layered analysis. And again, as we observed in the recent modulus data and LWD data, fine RCA and coarse RCA test sections provided higher elastic modulus values than thicker large stone subbase test sections. Here, 18-inch thick large stone subbase test sections provided equal or higher stiffness compared to conventional class 6 and RCA wrap mix test sections. And the large stone subbase is built with geosynthetics, again had consistent results with the previous test sections. And then previous test results, I'm sorry. After paving, before any traffic load was applied or few traffic loads were applied, we analyze the falling weight deflectometer data again, and then we look at again the third load both for composite and layered analysis. The fine RCA and coarse aggregates by far showed the highest stiffness, and after paved, the thicker large stone subbase test sections performed almost equal and made better than coarse RCA and equal to fine RCA test sections. And class 6 limestone test section and RCA rep test sections had almost identical stiffness to the large stone subbases built with geosynthetics. So when unbound stiffness analysis, it was these large stone subbase test sections with geosynthetics perform a little bit lower, but once the road is paved, they kind of bounce their performance in a higher level. So overall summary, of course, as I described, the GPT is the gas permeameter test results, permeability, coarse RCA and RCA materials overall, except fine RCA, showed the higher permeability. And in terms of LWD results, fine RCA and coarse RCA were the highest, provided the highest stiffness than the class 6 limestone material and 18 inches large stone subbases. Then 9-inch large stone subbase test sections performed provide lower stiffness. And when we come to the APTLT, intelligent compaction resonant modulus data, and the FWD elastic modulus data, again the results compared to LWD and between IC and FWD results were consistent. Fine RCA and coarse RCA provided the highest stiffness. Large stone subbases, thicker large stone subbases were better in terms of performance compared to RCA rep mix test sections and limestone class 6 and class 5 test sections. And just said the 9-inch thick large stone subbases with geosynthetics seem to have lower stiffness for the timing, but again with paved results, it really showed that maybe it will perform superior or equal in time. So task 5 and task 6 will provide good information on that for us. And currently we are working on task 4 majorly, and we are collecting the data from MnROAD test facility for the field test results. And at Iowa State University, our main focus on these index properties that are listed here, and at University of Wisconsin-Madison, we are focusing on the soil water characteristic curve and hydraulic conductivity values. And this is a picture of the water retention characteristic curve tests. And these are the pressure plates that will be used for some of the finer, like fine RCA and subgrade materials that are collected from MnROAD test facilities. And this is a specially modified permeameter to run constant head on large size particles like coarse RCA or RCA red mixtures that doesn't allow head losses to happen a lot, so provide really reliable permeability test results. And Wisconsin so far working on this and finished the class 5Q permeability test results, and as you can see, the hydraulic conductivity of these materials changes from 10 to the minus 2 centimeter per second to 5 times 10 to the minus 2 centimeter per second. And some of the suction valve suction versus volumetric water content characteristics of the class 5Q materials. And they, again, we've been working on other materials so far, but the data is not available currently. And we are almost done with the standard gradation tests for the materials that we collected, and start doing some image analysis, taking especially for the large stone subbase test sections first to determine their gradation. And we are going to calculate the angularity and roundness, sphericity of all these aggregate materials that we collected. And we will do both 2D and 3D particle shape analysis. And this is a kind of schematic diagram of the image station that we modified currently, and we start taking pictures already. So we will hope to have that data in a month, in a couple of months, some data to show to an NRRA team. Sorry, this is the end of the presentation. I had to go very quickly. I hope it was clear.
No, Bora, you did a great job, especially all that material you had to cover, so thank you very much.
Right,
is there any questions for Bora out there? We got a couple minutes here.
There's a question online from Tom, which is, how are the test sections performing based on distress surveys?
Good question. It is under task 5. We are collecting that data, but we didn't digest it or summarize it yet. But we are looking into the distress surveys on the pavement surfaces, but we don't have the summary of that data yet.
I guess quickly, after driving over this morning, I don't believe there's any cracking in any of those test sections yet. Again, we did have some early issues where we had the geosynthetic put down early on in construction, but we don't see any of that coming through right now. So unless there's any other thoughts on that. Any other questions? I guess one question I'd have, Bora, is there anything that's right now you've seen so far that's kind of surprising to you? That's something that you didn't expect, or is it all kind of falling in line with what you expect for these two studies that are going on?
The large stone subbase test sections with geosynthetics, it was a surprise to everybody. We didn't see a direct contribution, but then when we think more about it, and within our group, ourselves, ISU and UW Medicine, with the team, and also with the NRRA Geotech team and with you guys, I think the current test methodology doesn't really help us to understand to really see the actual contribution of these geosynthetics. It is there, definitely they are contributing, but current test methods, FWD or APLT, doesn't help us to see that. So it was a little bit surprising, but for everybody, not only to us, also the geotech team. But I think now we really understand what the challenge is. And after the paved FWD analysis, we realized, they're not actually that weaker. So we hope to get more information on that in the task. But other than that, everything is aligned pretty well so far.
Okay. Yeah, I see that too. So I think we're going to move on. Thank you, Bora, for your time today.
Thank you.
Our second presentation today is going to be Manik Barman. from the University of Minnesota Duluth. He's going to be talking about the performance benefits of fiber reinforced and concrete pavements and overlays. So they have a test section on the low volume road that Manik and his team are going to be looking at. So not taking any of Manik's time, Manik, go ahead with your presentation.
All the cells and their properties. So you can see from 506 through 806, these cells have different quantities of the fibers. You can see the area highlighted with yellow. So 506 has plain concrete, and then the 606, 706, 806 has 3 different doses of fibers. Slab size is 6 feet by 6 feet. Thickness was supposed to be 5 inch for all the 4 cells, but accidentally 606 got 6 inches of slab, 6 inches slab. 139, 239. 139 is basically the city street design, like with a very ultra thin slab, like 3 inch, 6 feet by 6 feet slab. And then 239 was 4 inch, 6 feet by 6 feet slab. Okay. And then 705 and 805s, these 2 cells deals with investigations about the slab size. So cell 705s, basically large size slabs, and then 805, 6 feet by 6 feet slabs. Okay, so we are investigating if fibers fibers allow us to increase the slab size. If we can increase the slab size, we have to have less number of joints. So that's kind of the benefits. Okay, next slide, please. All right, so this slide basically provides some information about the mixture. I'll not go into details, but I'll just tell you one thing here is with the increase of the fiber dose, they have increased the cement quantity. You can see for cell number 806, which had 11.7 pound per cubic yard of fibers, that has 430 pounds of cement. Okay, so, and then increase of the cement, and then the fiber volume was added, so they had to do something with the aggregate. So you can see on the right side of the table that decreased the fines aggregate basically, and also a little bit of coarse aggregate. Okay, the slump was 0.5 to 3. That's kind of the slump. And the picture here showing the picture of the fiber that was used. Next slide, please. All right, I think you click like 3 or 4, then. So this slide basically provides information on the structure. Okay, so can you click more, couple of more times? All right. Sorry about all those. All right. So this slide basically shows different sensors that were used. You can see joint opening sensors, dynamic strain gauge, then vibrating wire, and then temperature or thermocouple tree. All right, so also there were joint opening sensors. This is just a typical picture I just took from the construction document. You can go to the next slide, please. All right. So I see the title is not changed, but this slide, can you click one more time, please? In this slide, we are discussing the crack and spalling surveys. So crack and spalling survey was conducted in different dates. You can see in the month of May 2008, they have done some survey, and also in April 2018 there were some surveys. Okay, so when you go out and then you do some crack survey, And then when you look for some crack, sometimes you can get bored. You know, when these cells, they only noted some corner cracks, but sometimes you can have fun too. Can you hit the next slide, please? Next. Click next.
So that's showing 139. Next one.
Yeah, 139. So I will tell you about the 139. 139 actually got premature distances because of the construction traffic and the some cracks generated, and that you know, those cracks continued, and then that cell has to be replaced. So if you click Ben one more, and then I can see the picture of the distances that we have seen in cell 139.
Okay, I'm showing the broken out area. Do you want another click after this?
Yeah. Well, I think the very good. We missed a good, very good picture. But I will share the presentation, or you will see the presentations. You can see what has happened to cell 139. So all the slabs got shattered, and then there was kind of a rotting kind of thing. There were like 3.5 inches of depressions along the wheel path. So probably here you go. That's the picture I wanted to show. So you can see like what has happened to cell 139. All right, we can go to the next slide now. Cell 239 has seen corner cracks, and mostly corner cracks, 10 number of corner cracks, 2 longitudinal cracks. Yeah, you can keep going. We can go faster in these slides. All right. So this if you are seeing the heading as 239, it is not 239. It should be 705. So we saw some corner cracks, longitudinal crack, and then some transverse cracks. And in the next slide, if you see, can you click?
I'm on 805 right now on my screen.
Okay, all right. Then I'm glad that others are seeing, but I'm seeing like 239 still. Okay, so 805 received 2 corner cracks, 3 longitudinal cracks, 4 transverse cracks. So, yeah, can you go ahead?
Okay, I'm on 506.
All right, yeah, that is really helpful. So 506 was not having fiber. So this one you can see spalling. So lot of spalling. 1 transverse crack was observed, but 15 numbers of spalling. So this is the only cell where we saw spalling. All right, we can go to the next one.
606.
Yeah. So 606, yeah, there was a corner crack. You can go ahead, please. All right, so this is the kind of the summary. All right, Ben, you can click a couple of times since animation is not working. So in this, this is giving a kind of summary. You can see, so we did not, that's good, that's good. So you see on 239, which is, I did not include 139 because that has resulted completely different distress patterns, kind of slab shatter. So I did not include that one in here. So 239, we saw a lot of corner cracks, but otherwise it is really performing well. So 705, 825, they're really performing kind of equally, although the 805, which has a little smaller slab, got a little more transverse crack, but I would still say we have to wait to understand how this perform, if they perform differently or not. On the right side, that's what I was telling, on 506, which is plain concrete, you see this is the only cell which has seen a lot of spalling, 15 numbers of spalling so far. All right, and then interestingly that we can see as we increase the fiber, the decreases, the distresses or the cracking was decreased. So that's kind of a very good observation. So fiber is basically helping reducing the fatigue cracking. So, but we'll have to wait for performance in the next couple of years. Please, next slide. The faulting, So again, 139's faulting data will be erroneous, but 239's faulting, you can see we got some negative faulting, meaning that the lip slab is up. But again, we'll have to be watching what happens next. Can you go to this next slide, please? Few more click here. So faulting was for 705, 825 was not too much. Can next slide, please? The faulting.
I'm showing 4 charts. Fibers are decreasing faulting.
Yeah, so yes, I'm not seeing that one, but I can still, yeah, that's kind of, you know, so I think like to my understanding, fiber's great contribution in reducing the faulting. Okay, so you can see there, 806 received really less faulting. 606 and 506, they received 506 which didn't have fiber at all, so they received higher faulting. Can you go to the next slide, please? So this is the picture of a faulting, and the next click.
I'm showing the graph.
Okay, so the graph where fiber doses versus
Faulting.
Faulting, yeah, you can see like there is a kind of clear relationship here. So I think this is a very good finding from the first year observation. You can see like when we did not have any fiber, we had faulting, although it's not too much, but with the increase of the fiber, you see we are kind of getting rid of faulting, or faulting is significantly reduced. Next slide, please, slide number 23.
I'm showing 239.
Yeah, so these are like FWD test results. So the very first test results, you can see the FWD results on the very first day in the September was a little high, and then actually decreased, and then on the cell 239 outside, and again increased in the month of May. So there is something going on. Can you click
705, 805.
Yeah, 705 and 825. These, I don't know what's wrong with these two cells or the joints that we are looking at. Actually, you see the load transfer efficiency was really low. So if possible, we probably want to include a couple of more joints. Also, I would say like we probably can include a couple of dates in the peak winter or in the summer. So that's what I would say. Can you go to the next one? So the next slide, the next slide gives a really good observation. If you just, I will just request you to look at the 806 cell 806. You can see here load transfer efficiency is kind of constant on all the joints. So that's probably the contribution. So fibers not only increase the load transfer, but the load transfer can be kept consistent over different joints. All right, so that's another good finding. Yeah, go ahead.
Okay. We have 4 minutes now.
All right. So next few slides are basically discussing different sensors data that we have been analyzing. But in the interest of the time, I just would like to mention that we have analyzed temperature data. Okay, so we analyzed weather stations data. So and then we found out the temperature gradient for each cell. Okay, so that we are trying to correlate with the distances that we observed, and also those will be kind of the asset for our future analysis. Then we have also analyzed the vibrating air sensor, or basically the strain because of the environmental either temperature or moisture. So we have analyzed those. So we are also correlating with the temperature and all, and we already found very good correlation. we have also analyzed joint movement data. So the joint movement basically with respect to the very fast data collection day, so how joints are moving, either closing or opening with the temperature, those things we have done. We have also analyzed dynamic sensor data to see what kind of stress or strain is occurring in different cells. We are focusing on 139 to see like what kind of magnitude of the strain or stress it has gotten under the load. Also, we are investigating some FWD data of cell 139 to find out if there was void underneath the 139s to investigate. I know there was little drainage issue. The base was not super strong, so that's probably has also contributed to the failure of this pavement. All right, I think this is what actually I wanted to discuss. I'm really sorry about this technical glitch, but
right now I'm on temperature sensor, temperature gradient, and we got about 2 minutes left. So
yeah, sure. No, I think
you're gonna have to go to your conclusions pretty quick.
Yeah. Go to the conclusion. I already discussed what we have done with respect to the data collections.
Okay, concluding remarks.
Yeah, so the concluding remarks is, as you have seen, that fibers are really contributing in reducing the fatigue cracking. If you look at the cell 806, which has highest fiber doses, that did not have any fatigue cracking. But one observation is, probably the fiber that we have used, that kind of fibers, if we want to use, we need more. So the fiber which had, the cell which has 5 or 8 pound doses, that did not perform significantly different than the plain concrete one. But the highest dose, which is 11.7, that's really performed well. So we might want to try with some other fibers too. And then you have seen the faulting. Actually, I'm really happy to see like how fibers is decreasing the faulting. So that's kind of the information we see from here. Also, the difference between the cells 705 and 825, we did not notice a significant difference. We'll have to wait for data. So I'll take one or two quick question, or Ben, whatever you allow.
Yeah, quick question, and we got to move on to the next one. So is there any questions, Bob, you see online?
There are no questions online.
Okay, I think, again, Bora, sorry. Excuse me, Manik, sorry about the glitch, but we'll have to move on to our next presentation. So
sure, thank you very much. Hope you will share this presentation. So do you want me to send it to tab members?
Yeah, please do. And the other presenters, if you'd send your presentation to Bob and myself, why the next talk is going on, that might be helpful. Bob, what do I do for transferring this over to the next person?
Good morning, it's Hamid Sadati from CP Tech Center. I'm here and I'm ready to share my desktop to go through my presentation.
Okay, that sounds good. So our next presentation is Hamid. I'll be talking about the reduced cementitious material and optimizing concrete mixtures. So I'll let Hamid go from there. And let Bob and Hamid get the screens figured out.
Sure, I'm just...
Okay, Hamid, have you requested control?
Oh,
now we see something.
Something's loading.
Yeah, that looks good.
So you should have my first slide up on the desktop right now.
Yep.
Okay.
If you could maximize that, that'd be great.
Maximize. I'm trying to see how to maximize.
I think you do that in PowerPoint, how you show it.
I think those 4 icons in the left-hand corner, 1, 2, 3, 4, 5 icons, there's a half screen icon you might want to click on. Nope.
Why don't you go ahead with this?
Okay.
Yeah, we can see it fine.
Okay, good morning everybody, my name is Sadati. I'm a research engineer at National Concrete Pavement Technology Center at Iowa State University. Today I'm going to have a brief presentation and brief overview of the data we have collected for the first year performance of pavement cells cast with reduced cementitious materials content in MnROAD. I'm going to present on behalf of the PI of the project, Dr. Peter Taylor, who is out of country right now and who couldn't join the webinar at this particular moment. So the goal of the project here we're discussing was to see the feasibility of construction and to investigate the performance of pavement cells cast with concrete that is designed and produced with reduced cementitious materials content compared to the typical practice we have. And the goal was to see what are the potential effects that use of such concrete design, such new concrete materials can have on early age properties and workability and constructability of the pavement, what are the effects on mechanical properties and durability properties of the concrete, and what can be the potential long-term durability properties, and what can be the potential serviceability problems. So the overview of my presentation, I'm just going to have a brief overview of the project to introduce you the cells and the material property and the concrete mix designs. I'm going to have a brief overview of the laboratory data from testing materials and overview of the data obtained from in situ testing and the data obtained from embedded sensors, and some photos and some data from recent distress surveys, and a summary and conclusion of the data we have had so far. So the test cells that we are talking about here are test cell number 138 and 238 at MnROAD facility. We had two experimental cells. Cell number 138, the concrete used for casting this cell was prepared with 500 pounds per cubic yard of binder. And the second experimental cell, cell 238, was cast with a concrete that was prepared with 470 pounds of cementitious materials per cubic yard of concrete. We call them cells with low cement and lower cement content. And the data we have here are compared with the ones we got from cell number 524, which was kind of a reference concrete and reference cell for us. And the concrete used for construction of this cell was prepared with 570 pounds of cementitious materials per cubic yard. The two experimental sections, cell number 138 and 238, we had an 8-inch thick concrete pavement, and we had 1 1/4 inch double bars in joints. The joint spacing was 15 feet, and the width of the lanes was 12 foot. But the reference concrete, the joint spacing and the dimension of the panels were the same. The double bars we had were 1-inch double bars, and the thickness of the pavement was slightly less, was 6-inch thick concrete pavement. Experimental cells were cast over a 5-inch thick class 5 aggregate, but the reference cell was cast over a 16-inch class 6 aggregate base. Here is a summary of the concrete mix designs. Cells with low and lower cementitious material content, 500 and 470 pounds. We had a 0.42 water to cementitious materials ratio for these two cells, and we had 20% by mass of class F fly ash for the concrete used in these two cells. The reference concrete was cast with 570 pounds of cementitious material, a 0.4 water cement ratio, and 30% bar mass of the same type of fly ash. So the research tasks in this project we had included a literature review, 3 annual performance reports to monitor the performance of these experimental cells over the time, and some analysis on early edge properties and some analysis on durability issues of these concrete mixtures, the long-term serviceability, performance, and hopefully all these are gonna be combined at the end of the project, forming a structure for recommended specifications to be used by MnROAD and practitioners in rigid pavement construction for use of reduced cementitious materials content in rigid pavement construction. So I'm not going to go through the details for literature review. The report was submitted early 2018 to the Technical Advisory Committee, and we received some comments, improved the literature review report, and resubmitted it. Today, what I'm going to discuss is a brief overview of the annual performance report we had for the first year from casting these pavement sections. I have three main categories of the data to present here. The field testing data we got during the construction, laboratory data from testing the hardened concrete samples, and in situ measurements, i.e. the data from sensors, and the test that is ongoing with support from MnROAD technical staff. So the fresh concrete properties, the field testing we had, were focusing on workability of the concrete, air void system of the concrete, water cement ratio of the material using the microwave test, and investigating the kinetics of hydration using semi-adiabatic calorimetry, and also monitoring the maturity of the concrete mixtures. The second category, the hardened concrete data, we had the mechanical properties, we had volumetric stability, and we had durability of the concrete to investigate. Just a double check, you all can hear me well?
Yeah, we hear you fine.
Good, great, so I'll continue. And the third category of the data we had, data from sensors embedded in concrete pavement, and data about in situ measurement, falling weight deflectometer, ride quality index, and data from testing the pavement sections exposed to controlled traffic loading, and also data from embedded sensors that capture the effect of environmental conditions on these concrete pavements. Also, activation of the joints and monitoring the distress in investigated cells. So starting with the fresh concrete properties, the investigated mixtures, both low and lower cementitious material, we had proper air void system in fresh concrete. We had 6.5 and 8.5% air content in fresh state. And we had SAM number of 0.22 and 0.26 for these two concrete mixtures. The SAM number, or super or sequential air meter test, provides a good index of distribution of air void in fresh concrete. And in order for a concrete to have a proper frost durability, we need to provide a SAM number of lower than 0.3. which in this case, both concrete mixtures exhibited proper air void system. The only issue we observed here was data from microwave test to determine the actual water cement ratio of the concrete. For the concrete with lower cementitious material content, we observed that the actual water cement ratio was 0.44 compared to design value of 0.42. For the workability, we did the Vikeli test and the box test, both to investigate the response of concrete to an external source of vibration to see how the concrete is going to react when exposed to vibration, which is a big deal for us when we are going to cast rigid pavements. So the concrete with low cementitious material content, we had good workability indexes. The Vikeli index was 0.88, and we had a box test rating of 1, which corresponds to less than 10% of voids at the surface of sample being after vibration. And for the Vikeli index, we typically recommend a rate of 0.6 up to 1 inch per square root of second to have a good concrete that is responsive enough to vibration for slip-form paving. But in the case of concrete prepared with lower cementitious materials, i.e. 470 pounds of binder per cubic yard. The workability indexes were not that desirable. We had some problems with workability. The weekly index was lower than the desired rate. We had a 0.5 inch per square root of second weekly index, and also the box test rating was not that good. We had a rate of 2 to 3 for different sides of the test, which corresponded to 30 up to 50% voids on the surface of test specimen after vibration. The third category of fresh property testing we had was the calorimetry data and the maturity. The top graph presents the calorimetry data. We had 2 samples per concrete type, and it was observed that the concrete prepared with lower cementitious material is generating totally lower amount of heat over time during the first 24 and 48 hours of casting. However, no significant issues could be observed here. We couldn't detect, based on the data, any potential problems with setting or delayed setting or elongated setting time. No problems like that. And also the maturity data we got from the sensors were totally similar for both concrete types, regardless of the binder content. The figure here at the bottom part of this slide are the maturity data. We see the data is almost overlapping over time for these two concrete mixtures. The maturity data was also verified by comprehensive strength development. Especially at the early age, we see that both concrete types are presenting comparable strength values at early age, and both concrete mixtures reached the minimum of 3,500 psi at 28 days. The same goes for flexural strength values, where we observed that the both concrete mixtures, regardless of the binder content of 470 or 500 pound per cubic yard, exhibited a flexural strength of higher than 600, somewhere like 620, 630 psi at 28 days. The mixtures had comparable, I would say, modulus of elasticity value, slightly higher for the concrete cast with lower cementitious material, which was expected because of the higher proportion of aggregate in unit volume of this concrete, and comparable coefficient of thermal expansion, similar values for coefficient of thermal expansion. And the interesting thing here was the higher drying shrinkage value observed at 56 days for concrete with lower cementitious material. Well, we are reducing the binder content and we are expecting lower drying shrinkage. However, because we had higher water cement ratio in this mixture, we had a slightly higher drying shrinkage value for concrete with lower cementitious material content. Other than that, the mechanical properties were comparable for the two concrete mixtures. The durability data we had, we investigated the air void system of the two concrete mixtures in hardened state. Both concretes had very good spacing factor with 0.002 inch spacing factor obtained for both concrete mixtures, which correlates well with the measurements in fresh state. With the good SAM data we had for these two concrete mixtures, almost 1% drop in air content in hardened state while compared to the fresh state, which makes sense and which is what we typically observe. And the problem here was the potential for oxychloride formation. So we used differential scanning calorimetry test method to determine the potential for oxychloride formation for the binder used in these two concrete mixtures. With 25% fly ash, we had 0.18 and 0.20 gram of oxychloride per gram of paste potential for oxychloride formation, which is higher than the recommended limit of 0.15. Overall, I should say from the material properties point of view, The mechanical properties and the durability indexes measured for the two concrete mixtures were comparable. We had similar performance for these two concrete mixtures regardless of the binder content. And the main difference we observed was just the potential problems with workability, with the concrete prepared with lower cementitious material content of 470 pounds. But for the in situ measurement, we have different types of data here, which was, and the data was collected in collaboration with, and with support provided from technical staff and research engineers at MnROAD facility. I really acknowledge their support here. The first set of data I'm going to go through was the falling weight deflectometer data. Test was conducted at 3 load levels of 6, 9, and 12,000 pounds. And the test was conducted on different slabs from lower cementitious material and the reference cells, both the inside and outside lanes exposed to traffic or not exposed to traffic. And test was performed at different spots of the slabs. For all these spots, we got the data, we developed the deflection basins, and based on the data obtained from testing the pavements before and after the joints, we tried and determined the load transfer efficiencies for these concrete mixtures for these pavements. Here in this slide, I have a summary of the LTE values we obtained for the three concrete types. Okay, starting from left, concrete prepared with low cementitious material 500, concrete prepared with lower cementitious material 470, and the reference concrete 570 pounds per cubic yard of cementitious material. The blue marker points here are presenting the data obtained from inside lane, which was exposed to traffic, and the red dots are presenting the data from outside lanes, just exposed to environmental loading, no traffic load. Comparing the data for the two experimental pavement cells, cell number 138 and 238, we had really comparable performance for these two pavement types, regardless of the binder content. The LTE values were ranging from almost 80% to 95-97% for these two concrete types. And it's interesting to see that there is a slightly high scatter while comparing the LTE values for the approaching and the departure traffic for these two concrete mixtures for the lane exposed to traffic load. But for the outside lane, which is not exposed to traffic, the departure and the approach traffic loads were more, I would say, comparable. We had a less extent of variation in these two. And the graph on the right side of this slide is presenting the data we have for the reference cell. The LTE values are slightly lower, starting from somewhere like 75% up to 93-94% LTE for the departure and approach traffic. However, we should note that cell number 524, the reference pavement, had a thickness of 6 inch compared to 8 inch thickness for experimental sections 138 and 238. Overall, I should say the LTE values were comparable for the experimental sections, and these are just the values we have had for the first year performance, and they are gonna serve as kind of a baseline for us over the time. We will keep gathering the data, and the MnROAD staff are gonna collect the data and send us data. We will review the data together and compare them with the first year performance over the time. A second series of the data I have here are the roughness, the right quality data. I have the MRI values, the average IRI values for the left hand side and right side of the lanes here. And the data was, the test was conducted using MnDOT's lightweight profiler according to ASTM E950, and received the data from testing at different times in 2017 and 2018 up to almost 1 year age of these pavement sections. All these 3 sections were cast in July 2017. So data we have here starts from for the experimental section from July 2017 up to July 2018. Top 2 graphs, cell 138 low cementitious and cell 238 lower cementitious. Again, the blue lines are representing the inside lane exposed to traffic, and the red lines are presenting the data from outside lane not exposed to traffic. Overall, the MRI values we have here are really comparable for these 2 concrete types, regardless of the binder content. It seems that there is a slight increase in MRI values for the second half of the first year measurements. There seems to be some increase, but we will just continue monitoring the IRI values and see the trend in increase in IRI for these concrete mixtures. The bottom graph here, and the graph we have at the bottom of this slide, we have the MRI values for the reference concrete. Again, the blue lines are inside lane exposed to traffic, and we see there is a clear linear trend in of increase in IRI values over time. Means reduced surface quality and reduced ride quality for reference concrete over time, which will definitely have something to do with the lower thickness of this concrete, 6-inch versus 8-inch compared to the 2 other sections. Again, these numbers are the first year data and are going to be baseline for our future measurements, and hopefully over time we will have further measurements and we can further investigate the effect of variation in binder content on ride quality and serviceability of these pavement sections. Also, these pavements were exposed to controlled traffic loading. 18-wheel semi-tractor trailer of MnROAD was used to load the pavements, and data was gathered using a data acquisition system at 1200 Hz frequency. Readings were done at 2 speed levels of 5 and 35 miles per hour. And here I have a sample graph. Because of the high frequency and the nature of the test and nature of the sensors used, there is some noise in the data. But in addition to recording the maximum and minimum strain values, we also decided to go for the trend line here to capture the trend line and the kind of response of the pavements to control traffic loadings. So here's some typical data we got from these 2 experimental cells. Top graph, we have the data from cell with lower cementitious material content from sensors at top and bottom at mid edge of a instrumented panel. We can clearly see the loading pattern. We can clearly track the axle locations and the magnitude of load underneath the front and rear tandem axles. And we see that there is a symmetric kind of trend in strain and deformation for the top and bottom of the pavement. And overall, I should say the sensors located at similar spots of these 2 pavements, these 2 concrete types, had comparable performance, and the sensors were exhibiting similar actually a scale of the data, similar extent of deformation and strength under traffic loading. The strain we captured here on average were limited to 15 to 20 macro strain in most cases during the traffic loading, and there was no real significant variation in trend of deformations with speed or the concrete type here. We also monitored the data collected from vibrating wire strain gauge sensors embedded in different depths and different spots of these pavements. Okay, and it was interesting to see that the direction of the strains and the direction of deformation is following the pattern of variation in environmental conditions, environmental temperature. After like 75 days of casting, the cold season kind of started, and there was a trend for drop in environmental temperature, and this coincides with the time that the deformation patterns change. Again, we had comparable data. We had similar data for sensors located at similar spots of these two experimental pavements. And overall, the in situ strain values were limited to like 40 microstrain over the first year. And I should note that the numbers we have here are a combination of the effect of environmental conditions, variation in temperature, relative humidity, curling and warping of the pavement, and also shrinkage of the material itself. Overall, we had comparable numbers, comparable total deformations and maximum deformations for these two concrete types, regardless of the binder content.
Hamid, we
Yes,
have
sir.
about 3 minutes left. Could you
Sure.
kind of start getting to your conclusions? You have a lot of information to share, and I'm sorry to cut you short.
Sure. I'm going to go through the distress survey. February 2018, we noticed a transverse crack in concrete pavement cast with lower cementitious material content, and this was followed by some spider-like cracks in July 2018. So a few weeks ago, we went there to MnRROAD facility, and with support from MnRROAD technical staff, we took course to investigate the reason for these cracks. It turns out that the main transverse crack we had here was due to some utility line underneath the pavement. But it was interesting to see that in one of the core locations where we had the main distress, there was a segregation of concrete, even in concrete with lower cementitious material of 470. The cores are under investigation right now. We are measuring the resistivity, and we are trying to take a look at the concrete properties here. But this is an image of the place that we had the main distress. You can clearly see that the top part of the concrete, there is actually no coarse aggregate to restrain the shrinkage and to control the deformation. So that led into cracking. And some slight problems with finishing the surface in concrete with lower cementitious material content, which was kind of expected based on the workability data, but not such problem in concrete with low cementitious material. Excellent surface texture and excellent performance after 1 year. And the only problem we had here in cell 138 with low cement was kind of a diagonal crack in one of the cells exposed to traffic loading, which I think is the reason is something structural because of the loading, not the material properties here. So in summary, I should say that based on the first year data we have gathered up to date, the concrete mixture prepared with low and lower cementitious material as low as 470 pounds, there was no mechanical, there was no issues with mechanical properties or durability of the concrete itself. A bit concerned about workability of such a concrete, but overall the in situ measurement suggests that we have comparable performance with low cement with 500 pounds per cubic yard, and we will keep monitoring the data and update you with further data we get. But overall, so far, both pavement sections are performing well and as expected. And at the end, I just need to acknowledge the financial and technical support provided by Minnesota Department of Transportation, National Road Research Alliance, and also the great support provided by the technical staff at MnRROAD. And also, I should acknowledge American Engineering Testing for helping us with data collection. With that, I would say this is my presentation, and if there is any questions, I would be happy to take.
All right, thank you, Hamid. Are there any quick questions out there?
There's a question from Bernard.
Yes, sir.
Okay.
Let me get a microphone to him.
All right.
Dr. Hamid and Dr. Sadati and Dr. Taylor, here's my comment. Good job.
Thank you so much for your support, sir.
Yeah, how can you react to that?
Wouldn't be possible with your help.
All right. Well, again, this presentation will be on the NRRA website for this project, so we'll be getting those put on there shortly. We'll move on to our fourth presentation this morning. Joe Korzilius from SRF will be talking about maintaining poor pavements and the work that he's doing in that area. So we'll get that changed over. Again, this is the fourth and final presentation for this morning. Then we'll be reconvening at 1 o'clock Central Time to go through the last four presentations this afternoon from 1 to 4. So again, thank you for your participation. So Joe, can I hear your voice?
Yep, I think you can hear me now, right?
Yep, you sound good.
Can you see the slide?
No.
We're getting there.
How about now?
You gotta use your magic wand, I guess.
I did request control,
Okay.
and I haven't heard back yet. So
You should. You're a presenter, so you shouldn't have any problem.
okay. How about now? Can you see?
Joe, are you going down to the computer screen on the four icons at the bottom, clicking on that and saying present?
That's what I'm doing now. How about now? Can you see my screen now?
It's
Yeah,
loading.
something's loading. There you go. Looks good.
Okay, so it's working. All
Thank
right.
you.
Thanks, Ben, and here we go. This is so I'm going to talk about the poor pavement study, and this is a long-term research project, but it really is a project that's generated from data that is provided by the states themselves. So it really is. I think that's been the challenge on this job or this project is waiting for that data and getting that data. And so we're, hopefully I'll generate some interest based on the upcoming slides. So to further explain the project, the objective is defined at kind of identify the performance improvement and durability that can be expected for HMA pavements that are already in poor condition from the application of a thin pavement treatment. So we're looking at, we've kind of defined thin as 2 inches or less, or it really falls in a lot of the treatments done in the preventive maintenance category. But instead, as you can see by the chart I have here, classically we do preventive maintenance to maintain a good pavement in good condition for much longer. That's where we get a large payback for our dollar spent. Well, what we're doing with this project is we're doing those same treatments, but we're applying them when we already have a pavement condition that's considered poor. So if you look at the red line near the bottom, what we're trying to do is we're really looking at what are the improvements we're getting, how much improvement, how long do those improvements last, and what do those improvements cost, and are they cost effective as opposed to reconstructing or major rehabilitation. So that's kind of what we're trying to do, is balance out the difference between, is it cost effective basically to limp a road along as opposed to reconstructing. So as an example, I think this is one of the, I think this is the Missouri project. They sent a picture. I can't be sure, I forget. But so we're trying to define what are the practices used by the states. What are they doing? So I think the states or your maintenance groups, local cities are doing these things, but they're not really doing them and tracking them, so to speak. So I think the test sections are out there. It's just finding those test sections, grabbing the data from those sections, and then really kind of summarizing them and see what kind of performance we're getting, and are we getting value out of it? And ultimately, are we getting any value, and what is that value? So what are the results we are getting? And then summarize those practices and compare that performance to cost. So what's the life cycle cost of doing these things when you have a pavement that's already in poor condition? We are typically going to be focusing more on the low volume road end. I think if you're on a high volume interstate roadway, these things are not going to necessarily last. But whatever a state has in terms of data, we definitely want to include it, even if it's a higher volume. So I certainly don't want to eliminate or reduce that opportunity there. So we completed a literature review in early 2018, and our next step is to put out questions, which we did also in early 2018, back in April, May, and we've only got results back from a couple of states. With respect to the literature review, we went through and we found a couple of good reports that are really focused on that. We were looking at what has been done nationally and internationally to manage pavements that are in poor condition. Where have others used thin surface treatments as a stopgap measure or to extend the life of a pavement in poor condition? And then as part of that, we did establish those definitions where we said thin was a treatment of 2-inch up to 2-inch thickness, or less than 2-inch thickness. So if it hit 2 inches, it was not considered, we don't want to consider that necessarily in this study. 1.5 inches, yes, a quick kind of overlay type thing. And we also are looking at multiple treatments too. So if you did 2 treatments versus 1, we are considering that as well. So it could be patching and a chip seal. It could be a mill and a thin lay. Any of those types of things. We are looking at both. And I would say even what we're looking at, we're kind of focusing a little bit on IRA. So there was one very applicable study that's ongoing now that basically was finished. And I think you have some members working with some folks that are doing this study down in Iowa, and it is really, they are developing strategies for maintaining lower volume roads that are near the end of their service life, keeping them at a satisfactory level, and delaying that expensive rehabilitating and reconstruction. So they're pushing that reconstruction cost off, and that really is what we're looking at here. We're looking at, in a broader sense, what other states are doing, so based on existing data. We're not going to manufacture isn't the right word, but we're not going to manufacture test sections from which to collect data. We're going to see what people are already doing, what they've done, and then we're going to try to summarize that. Down in Iowa here, they have selected some strategies, they've applied them, and now they're monitoring them. And I think they're actually near the end of that, but they've extended that study to do some concrete reviews as well, I believe. So what they have found, though, at least preliminarily here in this thesis, is that these strategies, they refer to them as holding strategies because they are holding the pavement in place, that they can be successful more often in a combination. So looking at a thin mix overlay and a surface treatment in place, and they included full depth reclamation or reclamation, so cold in place recycling. That isn't part of what we're looking at. So they are doing, I would consider those significant rehabilitation types, but they are looking at those as part of this study. I don't believe this study is final yet. They've added a phase 2 before they finalize it, but I think they've got quite a few results that can be shared. Their other study is a cost-effective means of managing pavements in poor condition. This was done in Wisconsin, and I think MnDOT was part of this through the National Center for Freight Infrastructure Research. And in that study, they wanted to identify treatments or materials that could be used to extend the service life of pavements in poor condition. Similar approach, and they were looking for creating tools for analyzing whether it's a good approach or not. What should more or less almost like a selection table. Should I be doing this, and which would work best based on the conditions that I have? And then make some suggestions on those design strategies, more or less through a selection table. So I think both of these studies, in terms of, it's kind of interesting, there are states adjacent to Minnesota here where I'm at, and kind of in our region where some of this work is being done. I did not see much else outside of those two studies that are almost identical or very similar in terms of what they're doing. So again, the Wisconsin report focused on the identification of treatments and materials, and then they're looking at evaluating performance by economic, environmental, life cycle cost analysis. So as I said, very similar study in the intent. So here's where we are now. We put out our questions last spring, April, May, and we've got actually only 2 states that have responded. It'd be good to get other states that respond, and hopefully if I can demonstrate what we've done with the data that I did get, I think that'll kind of spur some additional interest in this. And it's really looking at this from a very simplified perspective, Bernard. So some of the questions for data gathering we put out in May, and then we want to compile the performance data and cost data, and it's kind of focused on the member states. And then we're going to identify, going back to that curve, the performance improvements, the durability, and the savings. Is there any kind of savings? So we had responses from Missouri and Minnesota. Missouri looks at in their pavement management system, so we're looking at what they have. They measure RII at highway speeds and pavement distresses. They rate on a scale of 1 to 10. Minnesota also uses IRI, and I think that's pretty universal, and they have a system where they're using the structural rating for the cracking, for those kind of distresses, and then they summarize everything in a pavement quality index. Just a calculation, a couple of calculations based on visual distresses measured, and kind of a summation of the PQI would be a summation of the IRI and the structural rating. So some of the questions we put out there is, how does your state identify poor pavement? Now we'll come up with a standard for the states that in this report, but I think I wanted to get a kind of an idea of how people are defining that. Missouri, that's a little bit, I don't want to say a moving target, but it's adjusted for the type of road or the level of traffic and level of service that's expected for that road. MnDOT looks like they keep theirs pretty standard regardless of the road. And then they probably take that into account in their other planning processes. Either approach is good. So we requested that the states provide pavement test sections of roadway that are in poor condition where a thin surface treatment was applied. So this is an example of what Missouri provided. I think on the left side you can see it's in poor condition. I apologize that they're kind of small photos, we're given the slide, but you have a lot of alligator cracking, but it's relatively smooth, probably some rutting in there. In 2014, that was 2013, in 2014 they applied a chip seal, and by 2017, as you can see, it's still in service. It's still providing, good enough service, but your IRI is now starting to creep up there again in 2017. So in 2013, it was 244. They were able to drop that IRI down, and now it's going up to 155. But that's not bad. Now, keep in mind the traffic ADT was reported on this at 250, so it's relatively very much low. But at a cost per 50,000 miles, I'd say this was fairly cost effective. They've already got 4 years out of it, 14, 15, 16, 17, it's 18. So I think it was very cost effective. And that's really the focus of the study, is the cost effectiveness of where to apply them and where not to apply them. I think that's really important, and making those judgments. And so if you're sitting you're sitting looking at your budget, and you're sitting looking at your alternatives, there are some roads where you're going to say this is a great alternative. Now this is one example. It's nice to get a number of examples. Minnesota provided 5 test sections here. They had 4 different applications, and then they provided an IRI based on what they were seeing beyond that. So we're looking at, year 4, I think those are 28, those are the last numbers, those with the red on them. The I-35 at the top there, I think that might have just been done, 2016, so I don't know if there's any follow-up data that was provided. But you can see that the application dates and the Cape Seal, that's performing pretty well. You can see what the IRI was before, how much improvement they got from that application, and then how it's changing with time. And I did also want to point out we do have the traffic numbers here, because I think those are important to striate where an application can provide a good performance and possibly where they won't provide good performance. And also the traffic levels typically might provide what the underlying structure is. Presumably the higher traffic levels are going to have probably a little bit better structure, even if it's in poor condition, but there's no guarantee of that. So that's another piece of information we asked for. And this is looking at the structural rating, so that's the cracking and how that was changing over time. There were some maintenance type patches, and I should have mentioned that with the IRI done at different times too. So that's all applied in here as well. So when I put that on a graph, the IRI versus time, and then kind of put the applications in there. Again, those applications have an application year, so delving deeper, I think we'd make some adjustments there. But how was that IRI and how was that structural rating changing? And that's just the base level data without kind of looking at it without, try to understanding why we're going up and down, things like that. So the reason I want to illustrate this is really what I think this study really is looking for. They want to get that comparison with the IRI with time and the cost effect and the life cycle cost. Did we get value out of that? I did take that IRI and calculate the RQI, and MnDOT uses this formula in their standard pavement management system, and I replotted those numbers on the scale, and then you can see I'm not sure what happened over here, but that is something to check and look at the data and find out. This is, I believe, a microsurfacing was applied twice. It looks like about 7 years apart. So, but that's one thing to delve into and see, ask those questions ahead of time. Again, I haven't got that deep into it at this point. Hoping to get more data to kind of look at, and certainly more surface treatment types, because you get different performance from different treatment types. And but we're not really looking at necessarily in depth why the roadway was in poor condition before, but presumably it's got structural issues as well, alligator cracking, potholes, as well as maybe rutting, as well as just a lot of roughness. So when we get this data, our focus is going to be on, as I've kind of mentioned a couple times, the initial improvement in the ride quality after the application, the performance. So that performance is, what's the rate of loss of ride quality over time? And that's going to be time related, but that's also going to be traffic related. We're going to compare treatments if we can. Maybe we'll lump some together after a while. We might lump, microsurfacing in with chip seals. It's hard to know at this point, but we'll do kind of a comparison between the different treatments, as well as if we kind of lump all the treatments together and kind of see what makes sense. And then the cost of those treatments, what's the benefit? And then what's the life cycle cost, so that we can kind of basically mathematically decide if this is a good treatment. And even if it's mathematically a good approach, that's probably not always going to be the best approach either. So keep in mind, these are low volume roads that we're typically using, but if as your volume goes up, you're going to want to get in there less and less. You're not going to, presumably with the higher levels of traffic, your performance is going to degrade much more quickly, and you're going to have to get in there more frequently. So there is a point of diminishing returns. It's kind of trying to calculate or figure out where that is. And then, but not make it the decision-making process, but make it part of the decision-making process. And then we're hopefully going to have a final report in May of 2019. And again, I just implore people to maybe look and kind of get back some additional data so that we can go with that. If we can get a half a dozen sections from each of the states, I think we'll have a pretty good grouping of data. And I apologize for being short, but that's where I'm at, I think, now for the study. So, Ben, I don't know if you want to.
No, thank you very much. You really helped define the project and where you're going at. And again, I think what Joe is really saying is he needs some more input from other states, other members, to kind of get a full view of the different types of treatments to finish this project. Any questions out there, Bob, that you see online, or any questions in the room there?
There are no questions online. Anything in the room?
Can you guys hear me? It's Glenn.
Oh, hey,
I
Glenn.
can hear you.
Good. Say, Joe, good job. It sounds like maybe the chair of the executive committee needs to send a note out to the states to tell them get you some data.
Well, I think the chair has done that before.
I think I'll do it again.
Okay.
Yeah, he's an awfully mean guy, but if we could get him to do that, that might help.
I'll put something together. Joe, if you could send me a little bit of verbiage, that'd be great.
I can do that, and I think I think it helps if you can see the direction too. That's what I was hoping to get out of this presentation here, is to say, here's kind of the direction we are going to go. Hopefully that's of interest to folks too, because obviously I think in our neighboring states it's some interest. Some work has been done on it, and I'm actually interested now that I've really started looking at the data. I think there's some cost effectiveness that can be, it just supports some decisions that maybe we're already making.
Yeah, absolutely. And we got North Dakota now too, so we can send it to them.
Oh, one more. Now,
yeah.
One more state, so that it'll be good. And it is probably a fairly, I don't know, Bob, you might be able to talk about how much work it is to get the data, but I forget who. But anyways, I think Elliot actually sent it to me too, so he may have done the work to put that together.
Yeah. Well, thank you for getting those two states at least, and we'll work on getting the contacts for North Dakota and kind of rustling them up a little more data for this, because I think this is one of the harder research in a lot of ways, because it's not like, doing the research on a test cell is fairly easy because it's there. This here, we're depending on others to get that information. So the more we get, the better results we'll achieve. If there's no other questions, I guess we'll wrap this up and then reconvene at 1 o'clock. We'll be talking about the asphalt overlays. We'll be talking about the partial depth repairs that are being done, along with the long-term impacts of early opening of concrete and the cold central plant mixed recycling. So that'll be our afternoon. I hope you all can join us after lunch. So thank you.
All right. Thanks, Ben.
Yep, thank you. Bob, I'll give you a call real quick.